Have you ever wondered if a mathematical statement can be true 100% of the time, false 100% of the time, or if it just depends on the specific situation? What we're going to do in this video is explore these three possibilities, which we call tautologies, contradictions, and contingencies. We'll think about how to use truth tables as a repeatable algorithm to classify any statement we come across. Now, before we dive in, if you want to revise your understanding on propositions and law of logical connectives such as conjunction, disjunction, implication, or by implication, you can watch our previous video where the link is put down the description. All right, now let's dive in. First up is the tautology. By definition, a compound proposition is a tautology if it is always true, regardless of the truth values of the individual parts. A classic example is either it is raining or it is not raining. Here on our example, we have two propositions. If we let P be it is raining, then it is not raining will be negation of P. Hence, our statement is P or negation of P. Now, let's look at the truth table together. If P is true, then not P is false. And since an OR statement only needs one part to be true, the result is true. If P is false, then not P is true, and the result is still true. Because that final column is all true, we have ourselves a tautology. Next, let's think about the opposite, the contradiction. This is a proposition that is always false, no matter what. A simple example is P and negation of P, or saying it is raining and it is not raining. Let me make sure I'm following this properly. For a conjunction, or and to be true, both parts must be true at the same time. But since not P always has the opposite truth value of P, they can never both be true. We can check by building a truth table. When P is true, negation of P is false, then their conjunction will be false. And when P is false, its negation will be true, and their conjunction will still be false. Therefore, as we can see, the final column is all false, which confirms it's a contradiction. Finally, we have the contingency. This is just a plain vanilla compound proposition where the truth value depends on the situation. For example, think about P and Q, or the implication P implies Q. If we look at the truth table for P and Q, it's true when both are true, but false in every other row. Because the final column has a mix of true and false values, we call these types of propositions contingency. The same goes to P implies Q proposition. It's not guaranteed to be anything. It just depends on the inputs. Therefore, if the statement is not always true or not always false, meaning when its truth value dependent on the input of each proposition, then we call that statement contingency. So the question is, how do we determine a statement is either a tautology, contradiction, or contingency? Here is your step-by-step method for classifying any proposition. The first step is to express the statement in a logical expression, because we don't always get the statement in a logical form. Sometimes we get statements in their natural language, and identifying the building block propositions and the logical connectives will be our first task to express the statement in logical expression. But if the statement is given by logical expression, then this step won't be needed. Second, we construct a truth table for the entire expression. Based on the number of propositions it contains, we determine how many truth value combination it consists by the formula 2 to the n, where n is the number of propositions. The next step is examining the final column, which represents the truth value of the whole statement. After we found out the final column truth value, we classify it. If all true, then the statement is a tautology, and if it is all false, then it means it is a contradiction, and if it is a mix, then it is a contingency. Now, let's see these steps being applied in determining whether a given statement is a tautology or a contradiction with a couple of examples. This should be fun. Here I have two expressions here on the screen. I encourage you to pause the video and try to build the truth tables for these before we discuss them. The first example is, if it is raining, the ground is wet, and people are carrying umbrellas, then it is not raining, or the ground is not wet, or people are not carrying umbrellas. The second one is, negation of P or Q, in parentheses, by implies negation of P and negation of Q. All right, let's see how you did. For that first one, the proposition is put with an English sentence. meaning you have to first express the statement in logical expression by identifying the indicative phrases. To jog up your memory, I suggest you go and watch the video we did on indicative phrases, where I put it in the description. Now, first, let's see how many propositions we have in the statement. As you can see, we have 3 propositions, which are P being it is raining, Q being the ground is wet, and R, people are carrying umbrellas. Once we determine the propositions, the next step will be determining the logical connectives. The sentence starts with if, meaning it is an implication statement, with a hypothesis, it is raining, the ground is wet, and people are carrying umbrellas, and a conclusion, it is not raining, or the ground is not wet, or people are not carrying umbrellas. Hence, the first part will be the hypothesis, and the second part, which is after the phrase then, is the conclusion. But both the hypothesis and conclusion are composed of multiple propositions. The hypothesis includes P, Q, and R with conjunction, and the conclusion consists of negation of P, negation of Q, and negation of R with disjunction. Therefore, the whole statement can be expressed as P and Q and R in parentheses implies negation of P or negation of Q or negation of R in parentheses. Now that we express the statement in logical statement, we can proceed with building a truth table for the statement. Since we have 3 propositions, we will have 8 possible truth-value combination by using the formula 2 to the power of 3, where 3 being the number of propositions. The truth value is constructed as shown. Now, when you look at the truth value under the last column, which is the truth value of the statement, it is almost all true except the first row. For that reason, the statement is considered as contingency rather than a tautology based on the definition we've seen earlier. The second example is negation of P or Q as a whole by implies negation of P and negation of Q. Now, this is in a logical expression form, therefore we can proceed to constructing a truth table. Since we have 2 propositions, we'll have 4 possible combinations. Therefore, the truth table will be as shown. Now, when we see the last column, the truth value is all true, meaning the statement is a tautology. Here, we can note a logical property, which is when 2 compound propositions joined by implication is a tautology, then the 2 propositions are said to be equivalent, meaning they have similar truth value for all possible truth value combinations. As we can see from the truth value, the 2 compound propositions, negation of P or Q and negation of P and negation of Q, have similar truth value in all 4 possible combinations. Therefore, they are said to be equivalent, and this is called De Morgan's law, as shown on the screen. So, since these propositions are equivalent, then by implication among them will always be a tautology, as we've seen on the example. Before we wrap up our video, let me leave you off with a couple of exercises for you to practice as we did at this video. Try them out and let me know how you did in the comments section. If any of the question cause a challenge, let me know and I'll cover it in my next video. And we're done! To wrap up, tautologies are always true, contradictions are always false, and contingencies are the it depends statements of the logic world. Hopefully that makes some sense and gives you the confidence to start classifying more complex logic problems on your own. If this walkthrough was helpful, go ahead and hit that subscribe button to keep mastering math and logic with us here at Rimetric Walkthrough. Thank you for watching, and I'll see you in the next one.